Netflix can read your mind or LinkedIn knows your next career move before you do? You open the app and there it is, a movie you didn't even know existed, but now you can't stop watching, or a connection request from someone you haven't spoken to in a decade. That's not a coincidence. It's the invisible magic of graph and machine learning working together behind the scenes. Think of graph as giant webs of relationships where every person, product, and idea is a point, and the connections between them are the threads. Your friend list, the products you browse, the places you check into, they all form patterns. Machine learning takes these patterns and learns from them, spotting links you might never notice yourself. It's how banks catch fraud before it happens, how social media suggests people you might know, and how scientists discover new drug interactions. This isn't just the tech, it's the hidden network powering our digital lives, predicting our choices, and connecting the dots in a way that feel almost human. And once you understand it, you'll start spotting it everywhere. So guys, if you want to see more content like this, do like, share and subscribe to the channel and hit the like button below. So without any delay, let's get started. Before we commence, here just a quick information guys. If you want to step into the world of AI and machine learning, Simplilearn's professional certificate course in GenAI and machine learning in collaboration with ANICT Academy IT Kanpur offers 11-month live interactive learning experience. This program combines theoretical knowledge with practical hands-on project, equipping you with expertise in GenAI, deep learning, natural language processing, reinforcement learning, and many more. You work with advanced tools like ChatGPT, DALL-E 2, TensorFlow, Keras, and Hugging Face on over 15 industry-relevant projects, gaining real-world experience. The course also includes masterclasses from IT Kanpur faculty providing deep insights into the latest AI advancements, just prompt engineering and large language models. And upon successful completion, you will earn a prestigious IT Kanpur certificate recognized globally to boost your career prospects. And with Simplilearn Job Assist, you'll receive support in connecting with top hiring companies. So whether you're aiming to upskill in your current role or breaking into the AI field, this course equips you with the necessary skills and credentials to succeed in the fast-growing world. So what are you waiting for? Hurry up and enroll now, and you can find the link below.
Before we get into the video, let's take a glance at what we are going to learn in the whole course. Initially, Introduction to Graphs in Machine Learning, we will learn what graphs are, their key components, and why they're essential in representing relationships. Then, we will see the applications of graphs in machine learning. Then we discover how graphs power social networks, recommendations, and logistics. First, we'll see choosing the right graph representation, understand adjacency matrices, adjacency lists, and edge lists. Then, node embeddings and approaches. Explore techniques like DeepWalk, Node 2vec, and GCN for learning from graphs. Finally, we will see PageRank and graph algorithms. Learn PageRank, graph traversal methods, and graph-based clustering. Let's start with Module 1. Now let's understand what is graph. A graph is a structure used to represent relationships. It consists of nodes, also called vertices. These are the entities like people, products, cities, or web pages. Edges or links. These are the connections or relationships between the nodes. Let's take a new example. An airport flight network. Imagine a map showing airports and flights connecting them. In this case, each airport is a node. Each flight route between two airports is an edge, a connection. Let's say there's a flight from Delhi to Mumbai. That's an edge between the Delhi and Mumbai nodes. There's another flight from Mumbai to Bangalore. That's another edge. Now, we've built a simple graph with 3 nodes and 2 edges. Now, let's understand the types of graphs using this example. Let's start with undirected graph. If you assume that every flight goes both ways, that is, if there's a flight from Delhi to Mumbai, there's also one back from Mumbai to Delhi, you can represent this using an undirected graph. The connection goes both ways. But in reality, that's not always true. Then, directed graph. Sometimes a flight goes from Delhi to Mumbai, but not vice versa, or maybe only once a week in the other direction. In this case, we use a directed edge to show that the flight goes only from Delhi to Mumbai. This makes it a directed graph, where direction matters. Then, weighted graph. Let's say each edge also carries flight duration. Delhi to Mumbai is equal to 2 hours, so edge weight is equal to 2. Again, Mumbai to Bengaluru is equal to 1.5 hours, so edge weight is equal to 1.5. Or you could use the cost as a weight. Delhi to Bengaluru is equal to 5,000. Mumbai to Delhi is equal to 4,500. These values make it a weighted graph, where the edges carry extra information that influences decisions. Now, you might be thinking, why is this useful? Let's see that. Airlines and travel apps can use this graph to, first, find the shortest path between two cities, then recommend the cheapest route with a stopover. Thirdly, predict congestion on popular routes. Finally, suggest alternative routes if one flight is cancelled. So, even in the world of flights and airports, graphs help model a very real, very complex system, and machine learning helps make it smarter. Now let's understand, why do we use graphs in machine learning? In traditional machine learning, data is usually structured in tables, like rows and columns in a spreadsheet. Each row represents one data point and each column represents a feature. But here's the problem. This structure treats every data point as completely independent. In the real world, that's rarely true. People influence each other. Products are often bought together. News spreads from person to person. Graphs allow us to capture these connections. Let's take a few examples. First, fraud detection. A bank account may seem fine on its own, but if it's part of a network of accounts transferring money in strange loops, the graph shows something suspicious. Then, product recommendations. Suppose 500 users bought both product A and product B. That means there's a strong edge connecting them. When a new user buys product A, we can recommend product B by traversing the graph. Finally, social networks. You're more likely to become friends with someone who shares mutual friends with you. Graph-based algorithms can predict this using link prediction. Graphs help us go beyond raw data. They help us understand context, neighborhoods, and patterns that we would completely miss in a spreadsheet. That's why graphs are so important in machine learning. Let's now explore how graphs are used in real companies: Facebook, Amazon, and Google. Let's now explore how graphs are used in real companies: Facebook, Amazon, and Google. Facebook has something called the social graph. Each user is a node, and each connection, like a friendship, a message, a like, or a comment, is an edge. This graph allows Facebook to power some of its core features. First one is friend recommendations. If you and another person have 25 mutual friends, Facebook uses link prediction to suggest them as people you may know. Next, community detection. Facebook can group users into clusters. For example, all your college friends might form one cluster. This is done using graph clustering algorithms. Then, feed ranking. Facebook uses edge weights, like how often you interact with someone, to decide whose posts show up first in your feed. All of these features come from analyzing how people are connected, not just who they are individually. Amazon uses a different type of graph. Here, the nodes include users, products, reviews, and product categories. And the edges could be user-viewed product, user-bought product, user-reviewed product. Let's say you bought a laptop. Hundreds of other users who bought that same laptop also bought a particular laptop sleeve. This creates a strong edge between the two products. Next time someone else buys that laptop, Amazon's ML model can easily traverse the graph and recommend the sleeve. What's even more powerful is that this can happen even if two products are indirectly connected. Maybe product A is related to product B, and product B to product C. Amazon can make multi-step recommendations because the graph structure captures all of these relationships. These graph-based recommendations go far beyond simple filters. They're based on patterns found across thousands or even millions of users. Google Maps is a textbook example of a graph in action. In this graph, nodes are intersections or key locations. Edges are roads connecting those points. Weights are travel time, distance, or even real-time traffic levels. When you ask Google for directions, it runs algorithms like Dijkstra's or A-star to find the shortest path from where you are to where you're going. But that's just the start. If a road is blocked or has heavy traffic, Google increases the weight of that edge. The algorithm instantly finds a better route. And with historical data, machine learning can predict traffic patterns. So even before you hit the road, the system can warn you about delays and offer alternatives. This combination of graph structure and machine learning gives us real-time, intelligent navigation. Now that we've seen how graphs are structured and used, let's look at what machine learning can actually do with them. Here are the most common tasks. First, node classification, predicting something about a node. For example, is this user a bot or a real person? Then, link prediction, predicting future connections, like whether two users might become friends or whether a person will buy a product. Next is community detection, finding clusters in the graph, like interest groups or fraud rings. Then, graph embedding, converting the graph into numerical vectors that ML models can understand. These vectors preserve the structure and context of the graph. Graph neural networks. These are deep learning models specifically designed for graph data. They can learn from both the features of nodes and their connections. This is where the real magic of graph machine learning begins, and that's what we'll explore in the next module. Hello guys, welcome back to the next module. After we have a basic understanding of graphs in machine learning, now let's dive into the applications of graphs in machine learning. First is social networks, that is, mapping influence with graphs. Think about Instagram for a second. Your account, your followers, the people you interact with, and the posts you like. All of this forms a graph. In a social network, nodes represent the users, and edges represent the interactions or relationships between users, whether it's following, commenting, liking, or sharing posts. Second, influencer identification. Imagine trying to figure out who the big players are in an Instagram fitness community. Graphs allow us to identify key influencers by examining the number of connections, followers, likes, comments. The more connections they have, the more likely they are to be an influencer. Graph algorithms, like PageRank, the same one Google uses, help rank these influencers. Now let's see how graphs help in social networks. First, analyzing user connections. When you look at your feed on Instagram, you're seeing the algorithm's way of understanding your behavior through graph theory. It looks at the people you interact with most often, the posts you engage with, and connects those to others who share similar interests. For example, let's say you follow fitness influencers and often interact with their posts. The algorithm will suggest other fitness influencers or brands, connecting you to a bigger fitness community, just like a recommendation from a friend based on mutual interests. Secondly, influencer identification. Imagine trying to figure out who the big players are in an Instagram fitness community. Graphs allow us to identify key influencers by examining the number of connections, like followers, likes, comments. The more connections they have, the more likely they are to be an influencer. Graph algorithms like PageRank, the same one Google uses, help rank these influencers. Let's take an example. You might find that someone with 100K followers isn't necessarily the most influential person. Rather, it's someone with fewer followers but a higher engagement rate, showing that they have a more connected network. Algorithms can help identify these influential figures. Finally, trend prediction. A great feature of graphs is their ability to predict trends. By analyzing how information or posts spread through the network, we can forecast what's likely to go viral. Take an example. If a fitness challenge starts gaining traction, the graph will show how quickly the challenge spreads through the community, helping platforms understand what content has the potential to blow up next. Practical application. Platforms like Instagram, Facebook, and Twitter rely on graphs for targeted advertising, showing you posts or ads based on your social interactions. The more information the platform gathers, the better it can target content to you. Second, we have is recommendation systems, suggesting what you love. Have you ever watched something on Netflix and it immediately suggests something else that you end up binge watching? That's no accident. It's powered by graph algorithms. How graphs power recommendation systems? They are, first is collaborative filtering. Imagine Netflix is trying to recommend a movie. It looks at the movies you've watched and compares them to other users who have watched similar things. If two users watched the same movies, Netflix assumes they have similar tastes and recommends movies that one of them has liked. For example, if you're a fan of sci-fi movies and someone else with similar taste watched a film you haven't seen yet, the algorithm suggests it to you, assuming you'll love it too. Second is graph-based collaborative filtering. Here, the interactions, like movies you've rated or bought, are represented as a graph where users and items, movies, products, etc., are nodes, and the ratings or purchases are the edges connecting them. Take an example. Amazon uses this in their Customers Who Bought This Also Bought feature. They analyze purchase history as a graph to recommend products based on similar purchase behavior. Thirdly, graph neural networks, GNNs. These are the next step in recommendation systems. While traditional systems look at isolated behaviors, like individual movie ratings, GNNs analyze the relationships between users and items as interconnected networks. This leads to more personalized recommendations. For example, if you've watched a bunch of sci-fi movies and someone with a similar viewing history has watched an action thriller, GNNs might recommend that movie based on the idea that users with similar profiles often enjoy it. There is a practical application. That is, companies like Netflix, Amazon, and Spotify use these systems to personalize content, enhancing user experience and driving user engagement. Finally, we have supply chains and logistics, optimizing deliveries with graphs. Supply chains are the lifeblood of businesses that deliver products, from manufacturers to end customers. But with so many routes, vehicles, and vendors, how do companies make sure products arrive on time and at the right cost? That's where graphs come in. Let's see how graphs help in supply chains. First is route optimization. Imagine a delivery service like UPS or FedEx. They have to figure out the fastest and cheapest way to deliver packages to a large number of addresses. Graph algorithms help find the shortest path between locations, reducing travel time and costs. For example, when a delivery truck sets out to deliver packages, the company uses Dijkstra's algorithm, or A-search, that is graph algorithms, to find the quickest route, factoring in distance, traffic, and even weather conditions. Secondly, the vehicle routing problem, VRP. This is about determining the best routes for a fleet of vehicles. It's complex, especially when dealing with hundreds or thousands of packages. In this case, each vehicle is a node, and the roads between them are edges. The VRP optimizes routes for each vehicle, ensuring the least cost for the entire fleet. Now imagine there are 10 different delivery trucks, each carrying different packages. The algorithm needs to figure out which truck should go to which route so that all packages are delivered on time without any extra fuel being wasted. Then, supply chain network optimization. Graphs help businesses model the entire supply chain, from suppliers to manufacturers to consumers. By analyzing this as a graph, companies can identify potential bottlenecks or inefficiencies in the system. For example, if a factory is waiting on a supplier to deliver materials, a graph can identify if there's a disruption in the supplier's network or if there's a delay in transportation. This helps companies adjust delivery schedules and mitigate risks. Then we have inventory management. Graphs also help with inventory flow. By modeling the flow of goods between suppliers, manufacturers, and customers, companies can keep track of where products are in the supply chain and predict shortages or overstock issues. Now let's see some real-world example. Amazon, known for its quick deliveries, uses graph algorithms to optimize the delivery routes. They factor in real-time traffic data, predict delays, and adjust delivery schedules to ensure packages are delivered on time. The real-world example is Amazon's last-mile delivery. The last-mile delivery is the final leg of the journey, from a distribution center to your door. It's often the most expensive and challenging part. How Amazon solves it. First is dynamic routing. Amazon's algorithm analyzes real-time traffic conditions, weather, and delivery urgency to adjust delivery routes. This ensures that packages are delivered as quickly as possible without wasting resources. Then, predictive analytics. Amazon also uses predictive analytics to forecast any potential issues in the supply chain, like delays due to weather. If an issue is predicted, it adjusts the route before the driver even starts their shift. Finally, AI and machine learning. Amazon uses AI to predict future demands, ensuring that warehouses are stocked in advance for expected product sales. They use graph-based models to optimize everything from product placement in warehouses to how they deliver goods to you. Now let's conclude. Graphs are powerful structures that help us model and understand complex relationships, and in machine learning, they drive improvements in everything from social media to supply chain management. In social networks, graphs help us understand connections, identify influencers, and predict trends. Then, in recommendation systems, they analyze behaviors and relationships to suggest content that's tailored to you. Then again, in supply chains, they optimize delivery routes and help businesses predict potential issues, leading to more efficient operations. By viewing real-world problems as interconnected networks, graphs, businesses, and tech companies can create better, smarter systems that make our lives easier. So, next time you're using a recommendation system or tracking a package, you'll know it's all thanks to graph theory. Let's move on to the next module. Hey there, and welcome to Module 3. Today, we're going to explore an essential topic when working with graphs in machine learning. How do we represent graphs in code? If you've worked with graphs before, you know how powerful they are for problems like social networks, recommendation systems, and logistics. But to make sure we can process these graphs efficiently, we need to represent them in a way that's easy for algorithms to work with. In this video, we'll break down 3 common ways to represent graphs. I'll explain each one step by step with examples and analogies, so by the end of this video, you'll know exactly when and why to use each type. So let's dive in. Let's start with the adjacency matrix. This is the most basic and straightforward way to represent a graph. Imagine a table or grid. You have nodes in your graph, and each row and column corresponds to one of those nodes. If there's an edge or connection between 2 nodes, we mark that cell in the table with a 1. If there's no edge, we put a 0. If it's a weighted graph, instead of just a 1, you might store the weight of the edge, for example, the distance or cost between 2 nodes. So the adjacency matrix is like a simple binary table where 1 means connected and 0 means not connected. But here's the catch. It's perfect for dense graphs, where most nodes are connected to each other. Let's say you're representing a small network of 4 cities, A, B, C, and D. Here's how the connections might look. First, A is connected to B and C. First, A is connected to B and C. Then, B is connected to A and C. C is connected to A, B, and D is connected to C. We can represent this as an adjacency matrix. Let's break it down. Row A shows that A is connected to B and C. Row B shows that B is connected to A and C. Then, row C shows C is connected to A, B, and D. Row D shows D is connected only to C. Now, when to use. First, dense graphs. The adjacency matrix works great for dense graphs, graphs where most of the nodes are connected. For example, in a social network where most users are friends with many others, this representation is ideal because most of the cells in the matrix will be filled with 1s. Fast edge lookups. If you need to quickly check whether 2 nodes are connected, the adjacency matrix allows you to do so instantly. You simply check the value at the intersection of the row and column representing the 2 nodes. For example, if you want to know if Alice, A, and Bob, B, are connected, you just look at row A, column B. If it's a 1, they are connected. Then, computational algorithms. The adjacency matrix is perfect for computational algorithms that work with dense graphs. For example, algorithms like Floyd-Warshall, which calculate the shortest paths between all pairs of nodes, perform well with this matrix, especially in dense graphs. Next, let's talk about the adjacency list. This is a more efficient way to represent graphs, especially for sparse graphs, where many nodes don't have direct connections to others. In this case, instead of a big matrix, each node has a list of its neighbors, the nodes that are directly connected to it. This method is memory efficient because we only store the actual edges, not every possible connection. So think of the adjacency list like a contact list on your phone. Each contact has a list of people they're connected with. In a graph, each node has a list of other nodes it's connected to. For example, let's take the same set of cities. Here's how the adjacency list looks for our example. Let's break it down. City A is connected to B and C. City B is connected to A and C. City C is connected to A, B, and D. City D is only connected to C. Now let's understand when to use this. First is sparse graphs. This is the go-to method for graphs where most nodes are not connected to many others. Think about a social network with thousands of users, but only a small fraction are friends with each other. Second is memory efficient. Unlike the adjacency matrix, we're only storing the actual edges, saving a lot of space. It is also great for algorithms like BFS and DFS. These algorithms explore the neighbors of each node. With an adjacency list, it's quick to find and explore those neighbors. Finally, we have the edge list. This one is the simplest and most straightforward way to represent a graph. It's just a list of edges, where each edge is a pair of nodes that are connected. If you just want to know which nodes are connected, the edge list is perfect. You don't care about the order or how many neighbors each node has, just the relationships themselves. For example, the same graph of cities, the edge list would look like this. Let's dive deeper into this. Alice is connected to Bob and Charlie, so we list the edges A, B, and AC. Bob is connected to Alice and Charlie, so we list BA and BC, and so on. Now let's see when to use this. Simple graphs. If you just need a quick list of edges, this is the most basic way to represent a graph. Then, edge-based algorithms. If you're running algorithms like Kruskal's algorithm for minimum spanning trees, you'll be working directly with the edges, so the edge list is perfect. Compact. The edge list is very compact and easy to understand, so it's great for small graphs or when you only need edge data. Let's now see which one to choose. Here's the quick guide. First is Adjacency Matrix. Use this when you have a dense graph and need to check connections quickly. It's fast for checking if two nodes are connected, but uses a lot of memory. Then, Adjacency List. Great for sparse graphs where nodes aren't connected to many others. It's memory efficient, but checking connections can take a little longer. Finally, we have is Edge List. The simplest and most lightweight, perfect for small graphs or when working directly with edges in edge-based algorithms. Choosing the right representation depends on the specific structure of your graph and what your algorithm needs to do. Think about the graph's density and the operations you'll perform most often. That'll help you decide which one to use. Let's move on to the next module.
Hey there! In this module, we'll dive deep into node embeddings, a powerful technique used to represent nodes like users, places, or objects in graphs as numbers, so computers can understand and analyze them. Let's start with the basics. Imagine you're using a social network like Facebook or LinkedIn. In the network, each person is a node, and the connections between them, like friendships, followers, etc., are edges. Now, in order for the computer to understand and analyze the relationships in this network, we need to represent each user node as something a computer can work with: numbers. Node embeddings are a way to turn each node into a vector that is a list of numbers. The goal is to make sure that nodes that are more similar to each other, like people who share many mutual friends, have similar vectors. This allows the computer to understand the structure and relationships in the graph. Let's say user A is friends with user B and user C. Using node embeddings, user A, user B, and user C will have vectors that are close to each other because they share similar connections. This helps the computer figure out that user A might connect with user B or user C more easily than with someone else who isn't connected. Now, let's dive into DeepWalk, which is one of the most common methods for creating node embeddings. Imagine you're taking a walk through the network, starting from one person, and you randomly pick one of their friends to visit. Then, you randomly pick one of their friends, and so on. This is called a random walk. DeepWalk uses these random walks to create sequences of nodes, like sentences in natural language. Just like how Word2Vec creates word embeddings by analyzing how words appear together in sentences, DeepWalk creates node embeddings by analyzing how nodes appear together in these random walks. Let's say we start at user A. From user A, we randomly move to user B, then to user C, and so on. These random walks generate sequences, like these sequences are treated like sentences, and DeepWalk uses a technique similar to Word2Vec to learn embeddings for each node. Now that we've covered DeepWalk, let's talk about Node2Vec, which is a more flexible version of DeepWalk. While DeepWalk relies on completely random walks, Node2Vec gives you control over how the random walk is done. The goal is that nodes that appear in similar sequences will have similar embeddings. Node2Vec introduces biased random walks, meaning you can decide whether you want to focus more on local neighbors like immediate friends or explore global relationships like friends of friends or even more distant connections. This allows Node2Vec to capture more complex relationships in the graph. Node2Vec gives you two options for walking through the graph. The first one is breadth first search. It focuses on exploring local neighborhoods, like only moving to user A's close friends. Then, depth first search, DFS, focuses on exploring global nodes, like moving to friends of friends or distant connections. By adjusting how much you focus on BFS or DFS, Node2Vec allows you to capture both local and global network structures. Let's say we're trying to predict whether user A will become friends with user D, who they don't currently know. Using Node2Vec, you can adjust the random walk. If you choose BFS, you'll focus on user A's immediate connections. But with DFS, you'll explore further connections, potentially uncovering hidden relationships between user A and user D. This makes Node2Vec much more powerful than DeepWalk for capturing both close and distant relationships in the graph. Next up, let's talk about graph convolutional networks, GCNs. While DeepWalk and Node2Vec rely on random walks to learn node embeddings, GCNs use a neural network to learn from a node's neighbors. GCNs work by aggregating information from a node's neighbors and using that information to update the node's representation. It's like learning from the people around you to make better decisions about yourself. Over multiple layers, GCNs combine information from the node's neighbors and create more informed embeddings. Next comes, how do GCNs actually work? GCNs work in layers. In each layer, the node aggregates information from its neighbors. For example, if user A is connected to user B and user C, the information from user B and user C will help user A update its vector. The more layers you have, the more neighbors information the node gathers, which helps the node learn richer, more detailed representations. Let's say you want to predict if user A is an influencer in a social network. If user A is connected to many influencers, the GCN can aggregate information from these neighbors and predict that user A is likely to be an influencer as well. The GCN gathers data from user A's neighbors to make this prediction.
GCNs are especially useful for tasks like node classification, predicting labels for nodes, or link prediction, predicting new connections in the graph. Let's quickly recap the techniques we've learned. First, node embeddings. Convert nodes in a graph into vectors that represent their relationships. Then, DeepWalk. It uses random walks to capture the local structure of the network and learns node embeddings using a word-to-vec-like technique. Then, Node2Vec extends DeepWalk by adding biased random walks, allowing you to focus on either local or global relationships in the graph. Finally, GCNs use a neural network to aggregate information from neighboring nodes and make predictions based on the graph structure. Then we have some practical applications. These techniques are incredibly useful in real-world applications. Here are a few examples. Social networks. Node embeddings can be used for friend recommendations, identifying influencers, and community detection. Then e-commerce. In recommendation systems, node embeddings help recommend products or content based on users' behavior and preferences. Now healthcare. Node embeddings are used to identify similar diseases or patients in medical networks. Then we have fraud detection. In finance, node embeddings can help detect fraudulent transactions by analyzing the relationships between different users or transactions. In this module, we've learned about node embeddings and how techniques like DeepWalk, Node2Vec, and GCNs are used to represent nodes in a graph as vectors. These embeddings capture the relationships between nodes, making it easier to analyze and make predictions about graph-based data. By using random walks, DeepWalk, and Node2Vec, or aggregating information from neighbors, we can create powerful models for understanding networks in social media, e-commerce, healthcare, and beyond. In this module, we'll dive deep into 3 key concepts in graph theory: PageRank, graph traversal algorithms, BFS and DFS, and graph-based clustering. These ideas are fundamental for understanding how things like search engines, social networks, and recommendation systems work. I'll explain them with examples and use simple, relatable analogies to make everything as clear as possible. Okay, imagine you are browsing the internet. You want to find the most relevant and authoritative pages for a topic, right? PageRank is the algorithm that helps Google do just that. It helps decide which websites should appear at the top of search results. Then come, how does PageRank work? PageRank is based on graph theory, where web pages are like nodes in a graph and links between them are like edges. In simple terms, PageRank works by looking at the links between web pages and assigning a rank based on how many important pages link to a particular page. Think of it this way. If you're having a party and someone popular invites you, you'll likely be seen as important. Just like if a famous website like a news site or an academic paper links to a blog post, Google will consider that blog post important too. Then come, why is PageRank important? When Google ranks a web page, it doesn't just look at keywords on the page. It also looks at how many other authoritative pages link to it. The more important pages that link to a page, the higher its rank in search results. For example, if a well-known site like Wired links to a tech blog, Google will give that blog a higher page rank. If a smaller blog links to it, that link is worth less. So, in summary, PageRank helps search engines understand the authority of a web page based on how many other important pages link to it. There are graph traversal algorithms. The first one is breadth-first search and depth-first search. Before we dive into the specifics of breadth-first search and depth-first search, let's break down what graph traversal means. A graph is a collection of nodes like people and edges like friendships. Traversal is the process of visiting every node in the graph. There are two main ways to traverse a graph, BFS and DFS. Let's first understand breadth-first search. How BFS works. Imagine you're standing at the center of a huge city and you want to know how to get to a friend's house. BFS starts by visiting all the immediate neighbors, for example, the houses next to you, then moves on to the neighbors of the neighbors and so on. It works level by level. Let us now focus on the steps of BFS. Choose a starting node, source. This is where the search begins. Mark it as visited so you don't visit it again. Put it into a queue. Then, take the first node from the queue. Remove the front node from the queue. This is called dequeue. Let's call this node the current node. Then, look at all neighbors of the current node. For each neighbor, if it has not been visited yet, mark it as visited. Add it to the end of the queue. Then, repeat the process. Go back to step 2. Keep taking nodes from the front of the queue and visiting their unvisited neighbors. Finally, stop when the queue is empty. This means all reachable nodes have been visited. The order in which you visited them is the BFS traversal. Now let's see, where is BFS used? BFS is perfect for finding the shortest path in an unweighted graph. For example, you're trying to find the shortest path between two people in a social network. BFS will explore all your direct connections first, then their friends until it finds the target person. And now, why to choose BFS? BFS is great when you want to find the closest node, especially when the graph doesn't have weights or complicated connections. Let's see depth-first search, how BFS works. DFS is like going deep into the woods. You pick a path and you keep going down that path until you can't go any further. Then you backtrack and try another path. In other words, DFS explores as far as possible along one branch before backtracking. So, the steps in DFS: Step 1. Start at the source node. Then, go deep down a path until you hit a dead end. Then, backtrack and explore the next path. Then, where is DFS used? DFS is great when you need to explore every possible path in a graph. Imagine you're exploring a maze. DFS will go down one path, trying to find the exit. If it hits a dead end, it will backtrack and try a new path. So, why DFS? DFS is better when you need to explore all possibilities and don't care much about the shortest route. Coming to comparison between BFS and DFS. BFS is level-based and finds the shortest path quickly, so it's used in things like finding the shortest route in a map, whereas DFS explores deep into a path, so it's used when you want to explore all possible options, like in puzzle solving. Graph-based clustering. Now, let's talk about clustering, which is the idea of grouping similar things together. In graph theory, clustering means finding groups of nodes that are more connected to each other than to the rest of the graph. Lastly, we'll discuss what is graph-based clustering. In graphs, nodes can form clusters or communities. These clusters are groups of nodes that are densely connected with each other but sparsely connected to other nodes in the graph. Think of it as grouping people in a large city based on shared interests, like a group of tech enthusiasts or fitness lovers. You could think of these as communities within the broader network. So guys, that's it. In this course, you've explored how graphs can capture and represent complex relationships, whether it's social media friendships, product recommendations, or optimized delivery routes. You started by understanding what graphs are, nodes, edges, and basic terminology, through relatable examples like social media connections and transport networks. You then uncovered why graphs matter, diving into real-world applications such as Facebook's social networks, Amazon's product recommendations, and Google Maps route planning. From there, you discovered how to apply graphs in machine learning, analyzing social networks to find influencers, powering recommendation systems like Netflix, and optimizing supply chains for faster, smarter logistics. You also mastered choosing the right graph representation, from adjacency matrices for dense graphs to adjacency lists for large, sparse networks and edge lists for simpler structures. Moving deeper, you learned node embedding techniques like DeepWalk and Node2Vec to represent nodes as vectors, and explored graph convolutional networks, GCNs, for advanced predictions. Finally, you explored powerful graph algorithms like PageRank for web ranking, BFS and DFS for graph traversal, and graph-based clustering for community detection. Most importantly, you now have the skills to think in graphs, to see connections where others see data, and to use this perspective to solve real-world problems with precision. This is just the beginning. Keep exploring, experimenting, and building with graphs to unlock their full potential in your machine learning journey.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.